Have you ever, really looked at the fabric of your shirt? Its creation isn't some simple, quiet process. No, it's a high-speed, perfectly choreographed mechanical ballet. We're talking thousands of threads dancing together, faster than your eye can even track, all to create the textiles that are literally all around us. Today, we're going to pull back the curtain on one of the most critical moves in that entire dance. You see, this whole incredibly complex performance, it all boils down to just three basic moves. First, you've got shedding. That's where the lengthwise threads separate to create a gap. Second is picking, which is all about shooting the crosswise thread through that gap. And third is the beat up, where that new thread gets slammed into place. And we are going to zero in on that crucial second step, picking. All right, so here's the game plan. We'll start with the basics of the weaving dance itself, then we'll define exactly what picking is. After that, things get fun. We're going to watch a classic mechanical showdown. Then we'll see how technology leaped beyond the shuttle. And finally, we'll look at what happens when the timing in this whole high-speed ballet is, well, when it's just a little bit off. Okay, so to really appreciate the star of our show today, the picking motion, we first need to set the stage. Let's do a quick recap of the foundational elements that make every single piece of woven fabric possible. It all starts right here. It's so simple on the surface. You've got one set of threads, the warp, stretched out tight, running lengthwise. And then you have the weft, which is the thread that gets to travel, weaving over and under the warp threads to build the fabric. It sounds simple, right? But making it happen at lightning speed is where the genius comes in. So, with those basics down, we can finally get to our main event. How in the world does that weft thread make its journey from one side of the loom to the other, hundreds of times a minute? Well, that critical, explosive motion is what we call picking. To put it simply, picking is just that, the action of inserting the weft thread through that tunnel of warp threads, which is called the shed. But it's a single, powerful, incredibly precise motion that has to be perfect, time after time after time. And for centuries, this was the hero of that story, the shuttle. Look at it. It's this beautifully crafted wooden projectile carrying a little bobbin of weft yarn. Its entire job is to fly across the loom, trailing that thread behind it. So the big question is, how do you make it fly? Well, the picking mechanism actually has three absolutely critical goals. First, obviously, it has to launch the shuttle with enough force. Second, it has to do it at a super specific speed, not too fast, not too slow. And third, it has to make sure it flies in a perfectly straight line. Any wobble, any deviation, and things can go very, very wrong. So, how do you pull off that perfect launch? In the world of classic looms, this question led to two totally different engineering answers. It created a classic showdown between two competing designs, the overpick and the underpick mechanisms. This chart lays out the trade-offs perfectly. On one side, you've got the overpick mechanism. It sits above the shuttle box, and it's generally faster, the speed demon. It's great for narrower looms and lighter fabrics. On the other side, you have the underpick. It sits below. It's a little slower, but it delivers a more powerful, solid push, which is exactly what you need for those really wide looms and heavy-duty fabrics. All right, let's take a closer look at our first contender, the high-speed specialist of the two, the overpick mechanism. Now, before we see it go, let's just look at the parts. The key players here are this vertical shaft and the long picking stick up top. As the main loom shaft turns, a cam down below gives a little push, which makes the whole vertical assembly pivot. And that causes the picking stick to swing in this huge, powerful arc way up above the shuttle. And here it is in action. Just look at that. It's almost like cracking a whip, isn't it? The picking stick sweeps across, smacks the shuttle, and sends it flying. It's this really elegant, big, open, powerful movement. Okay, so now for the other side of the coin. Let's check out the powerhouse, the one designed for the wider, heavier jobs, the underpick mechanism. You can immediately see how different the design philosophy is here. With the underpick, the entire system is tucked underneath the shuttle box. So instead of that big, sweeping overhead motion, this thing uses a whole different set of levers to give a much more direct push from down low. And when we see this one in motion, yeah, the personality is totally different. It's much more contained, more direct. It's a shove, not a swing. It might not have that same blistering top speed, but it's a more controlled, forceful launch, which is exactly what you want when you're trying to push a heavy shuttle across a super wide loom. But As incredible as these mechanical systems are, the thirst for more speed, more efficiency, it never stops. So engineering had to evolve. It had to move beyond just launching a block of wood back and forth. And this is where things start to feel like science fiction. To just shatter the speed limit set by a heavy shuttle, modern looms got rid of it completely. Today, the weft thread is inserted by tiny metal projectiles, or by these long, skinny rods called rapiers that actually hand off the yarn in the middle, or, and this is my favorite, by unbelievably precise jets of compressed air or even water. All of this amazing innovation is driven by that need for speed and absolute precision. But it also shows you just how high the stakes are. In a mechanical ballet this fast, what happens when just one dancer is a little out of step? Well, if the picking motion is just a fraction of a second too early, the shuttle tries to ram its way into the shed before it's fully open. The result? It scrapes against all those warp threads, snapping them, and it wastes a ton of energy fighting against them. Late picking, though? Oh, that's way more dangerous. If the launch is delayed, the shuttle enters the shed just as it's starting to close up. This can literally trap the shuttle in the middle of the threads, causing a violent, catastrophic collision. We're talking broken metal parts, bringing the whole operation to a crashing halt. And it's not just about timing, it's also about force. You have what's called a weak pick, not enough oomph to get the shuttle all the way across. But a harsh pick is just as bad. That's too much force, causing the shuttle to slam into the other side and bounce back, which can break the shuttle, the yarn, and damage the loom itself. It really is a Goldilocks situation. It has to be just right. And getting it just right is definitely not guesswork. Just look at the kind of math involved here. Engineers are using some serious physics, factoring in everything, loom speed, widths, the shuttle's mass, to calculate the exact amount of kinetic energy needed for one single perfect pick. It's such an amazing testament to the deep science behind this incredible mechanical art form. So we've gone from a flying block of wood to tiny metal bullets to focused jets of air and water. It's an incredible evolution. And it really makes you wonder, as technology keeps pushing forward, what invisible force could be next? What will the mechanical ballet of tomorrow's looms even look like?